Good afternoon, everyone. I hope you all had an energizing and fulfilling break after an insightful and practical morning. It's wonderful to see you all back here, ready and eager for what's coming up next. I am Manya Madhu, and I will be your host as we move into the afternoon segment of today's program. This morning, we had an immersive lab session that was focused on transportation engineering, where we engaged in practical applications of the concepts we have been learning. Practical sessions like this are crucial because they give us the opportunity to apply theory and observe how it interacts with real world variables. They are where our knowledge turns into skills. With that enriching experience behind us, it's now time to shift gears as we delve into afternoon's lineup. The second half of today's program will build on the themes of innovation and problem solving that we have touched on earlier, but with a greater focus on real world case studies, cutting edge research, and interactive discussions. Our next session will dive into topics related to transportation engineering, and I am absolutely thrilled to introduce to our esteemed speaker for this afternoon, Dr. Priyansh Singh. Dr. Priyansh Singh is an assistant professor in the discipline of civil engineering at Indian Institute of Technology, Indore. He has done his bachelor's in civil engineering from Jabalpur Engineering College, Jabalpur. He has done his master's in technology from Indian Institute of Technology, Guwahati, in transportation engineering. He has also done his PhD in pavement materials from Indian Institute of Technology, Delhi. Before joining IIT Indore, he worked for Billia Institute of Technology, Pilani. His areas of interest include payment modeling, design construction and evaluation, payment recycling, innovative materials and technologies in payment engineering, rheology and maintenance and rehabilitation of payments. I would like to invite our distinguished guest, Dr. Priyansh Singh, to the stage. We are eager to learn from his vast knowledge and research experience. Please join me in welcoming Dr. Priyansh Singh.
Okay, so I think from morning onwards, you must have been doing some testings on pavement materials, maybe on aggregate, maybe on binders, and maybe on some admixtures. So today, because of the limited time, I have just chosen one material of the transportation domain, which is very important as compared to any other material, any other component, and that is the binder. Binder, when I am saying binder, for cement concrete, the binder becomes cement, and for asphalt concrete, the binder becomes asphalt. Now this asphalt term I am using, you might not be aware of this asphalt term. This is same as you use bitumen. There's no difference between asphalt and bitumen. It's just a difference between terminology, what is being used in United States and in European region. Okay, so before going into this discussion, first let me introduce myself. So I am Priyansh Singh. However, your host has given a good introduction of mine. So, but I would like to introduce my teams also. They are at IIT Indore. So in IIT Indore, we have a small team which are working in the pavement materials, consist of me and my 5 PhD students along with some graduate students working with me. And we are trying to explore the green and smart highways, the effect of climate change on the pavement performance, the highway noise reduction, how we can reduce the noise of the highway because of the tire interaction with the highway surface. Also, we want to explore the connected and cooperative highway system, CITS, and also the community engagement and the equity distribution in the highway, because every highway project have almost most of the impact to the society from which it is going through, or the area it is going through. So this becomes an essential part. So currently our group is focusing on these all domains. They are here in IIT Indore. As far as today's discussion concerned, so we would be limited on these 3 IS codes actually. So these IS codes are IS 73 2013. I think you must have been aware of these specifications. This is actually the specification which gives binder grading or viscosity grading. The recent development happened in 2013 and later on it is also being revised in 2018, but more or less they are same. Then we have two latest codes comes on IS 15462 and IS 17079. They both came in 2019 and they are the code related with the polymer modified binders and crumb rubber modified binders. Don't get scared by the words crumb rubber or polymer modified. Later on we will try to explain what these things are. We all know how we get binder. So it is just a distillation process of the petroleum, whatever we extract, and we distill that. The heaviest part of that distillation is your bitumen. Mostly if you see the composition or chemical composition of your bitumen, so it mostly have carbon. Around 70 to 85% of the carbon it contains. Then the next major component is the hydrogen, and then we have sulfur, and then some traces of nitrogen, oxygen, nickel or some other materials. And if you see the composition how binders have, so we can by the SARA analysis we can see what composition your binder have. So it have saturates, aromatics, resins and asphaltenes. Mostly component which contains in the asphalt binders are the aromatic content, which may have around 50 to 65%. The least content you will find out around 20 to 25% or 5 to 20%, which are saturates and asphaltenes. And asphaltenes is the material which gives your binder the black or gray color. If you try to see all these components in the different fractions, so here you can see the saturates, aromatics and then asphaltenes and resin. Now, the introduction about binder is fine, but as a civil engineer, what we want to do with that binder? We want to make our roads out of that binder, and in order to make the road with that binder, we need to mix it with aggregate or any other material. Like you mix cement with aggregate, now that mixing happens because you add some water in it. But here in asphalt, in the case of asphalt, we cannot add water. Water will not liquefy your asphalt material. So instead of adding any water or anything, we use one technology, which is heating the binder. As you heat, the viscosity will decrease. Your binder will become more and more fluid. This is one technology. There are other technologies also. You must have been heard by about the tars, emulsion, or maybe some other materials. So those do the same thing, but they are different technology. Here today I am concentrated only when you are heating your binder. Now, whatever the existing binder we have, why we need any modification in the binder? So whatever the binder, when I'm saying a binder or neat binder or bitumen, it means it's just a raw extract what we got after the distillation from the petroleum product. Now that petroleum product is being cooked by the refineries in order to meet your viscosity grading, maybe VG 10, 20, 30, 40. But what happens, because nowadays the temperatures are reaching to extreme levels. We are seeing the temperatures of around 49, 50 air temperature. So that pavement temperature will be a little bit higher than that temperature. So that pavement temperature may be hitting around 53 or 55 degrees Celsius. Now in that temperature, if you just recall your softening point test, today you must have been done your softening point. What value you got? How much? 60? Which grade of binder you were testing? Which one? Cut back. No. Cut back is different thing. It's not a binder. Okay, anyhow. But if you see your softening point value for most of the neat binder will comes around in the same range which I am talking about. That means around 50 degrees Celsius or 55 degrees Celsius. That means at that temperature my binder is going to be soft enough to get deformed. So I need to make my binder more strengthened. I need to increase this strength so that it can take more stress, maybe thermal stress, or maybe the other climatic stress, or maybe other kind of stresses. So the modification, if you do, so whatever the modifier currently we are using, those are the waste material, maybe in the form of plastic, maybe in the form of crumb rubber, or maybe in the form of some other material. So whenever you are using some modified binder, that means you are helping in order to recycle some waste product. Now, because these binders are good to take more stresses, that means your pavement layer thicknesses will be reduced. That means your pavement will be more economic. And also, because binder is strengthened, that means the pavement life will be more. So there are multiple advantages of having modification in your binder. There could be different type of modification. That could be the chemical modification, any polymer modification, or the crumb rubber modification. Now here in this part of talk, we will only talk about the polymer and crumb rubber modified binder, not about the chemical modified binder. Now what happens? The polymer, if you see, what polymers are? Polymers are actually a chain. So whenever you will add a polymer into the binder, they will cross-link with it, and that's how they will increase their strength. So if you modify your binder, there could be different type of benefit. Some highlights of those benefits I have written here, summarized here in this slide. So they can improve the pavement performance in terms of improving the rutting resistance. What rutting is? Oh, this happens. Don't worry. We will explain rutting also in further slide. So, reduce fatigue cracking, improve low temperature cracking, reduce top down cracking, improve durability, and also increase the service life. Now, in order to understand the binder, first we need to understand what different scenarios my binder go through. So that I need to understand. Means if you have fever, you need to understand how your temperature is rising. Then only you will give the correct dose of paracetamol, isn't it? So similarly, we need to understand the different stages of binder. So those stages in case of binder is when your binder is at 0 degrees Celsius or at very low temperature. When the binder is at very low temperature, that means binder will be very stiff, very brittle. If you do load it anything on the binder, it will crack. And this type of cracking is taken as a thermal cracking. Here in this picture you can see all these cracking is because of low temperature. Whenever the low temperature will be there, the material will shrink, and also if there is any stresses that can be released in the form of crack. The next temperature, what binder is important for the binder, is the average service temperature. That is around 25 degrees Celsius temperature. Now this 25 degrees Celsius temperature is very important. If you want to connect this 25 degrees Celsius temperature with whatever test you have performed today. At what temperature you have done your penetration test? At 25 degrees Celsius, isn't it? And at what temperature you have done your ductility test? 27. That is as per the old code. Now it is being revised. We need to do the ductility test at 25 degrees Celsius on the RTF40A sample. So this average service temperature is the temperature which is actually the temperature in European and American region, the ambient temperature. But because we copy everything from European region, so that is why we have taken this 25 degrees Celsius temperature from there also. So we also assume that our ambient temperature, that means our average temperature, is going to be 25 degrees Celsius temperature, and this is the temperature when you will undergo the fatigue cracking. Now what fatigue cracking is? This is the cracking because of load. If you have number of repetitions of the load over the pavement capacity to take load will decrease, and whatever the stresses accumulate, that will release in the form of fatigue cracking. This is also known as alligator cracking. The next important temperature what your pavement will, or what your binder will undergo, is the maximum service temperature. This is the temperature which is around 50 or 60 degrees Celsius, 50 or 55 degrees Celsius maybe in India maximum. And if you see, this is the value around softening point. A kind of softening point also, the value you will get around 50-55 degrees Celsius. So this temperature is also very important, because at this temperature the pavement will undergo plastic deformation which will be unrecoverable, and that is known as rutting. So whenever you have the number of vehicles moving on the same path, they will make a gully like structure, and that is known as rutting. And this happens at the higher temperature. Also shoving, you might have seen this kind of plastic undulation on the pavement. This also happens because of the heavy temperature deformation or the high temperature deformation. Now the next important temperature which your binder will undergo is the temperature at which you will mix it with aggregate. That is going to be a 135 degrees Celsius or maybe 160 degrees Celsius, depending upon your mix design. So these all temperatures are very important in order to see the binder's performance, and that is why we have designed a spectrum of tests in order to characterize binder in all these temperatures. Now let's see what different tests are there in order to characterize our binder at these service temperatures. So the first test I am discussing about is at the high temperature, which is a drain down. Now whenever you are mixing your binder with aggregate, the binder and aggregate should not separate with each other. If it is separating with each other, it is called drain down. That means if you put your mix, binder will separate it out. That should not happen. This test is related with mixing temperature. Now let's discuss some other conditions also which our binder undergo. Now when you will get your neat binder from the refinery, the binder will have no aging. But when you will heat your binder to 135 or 160 degrees Celsius, binder will undergo some aging. After this heating, you will mix it with aggregate. At that time also, binder will remain at the elevated temperature. And again, when you will transport from the mixing plant to the field and compact, in this whole duration, the binder will be at the elevated temperature. And you know binder have resins and saturates. That means some volatile element. So if you heat it, some volatiles will be lost, and also at the elevated temperature binder may undergo an oxidation reaction, and that's how the stiffness of binder may increase. So the first instance, starting from your mixing till the laying, compaction, till the cool down at the field, this is known as short term aging. Zero, when we have no aging. Then mixing and layout, when we have short term aging. And then your road will have some service life. Service life might be of 15 years, 10 years or 20 years, depending upon your pavement design. And that aging we call as long term aging. So first let's see how to simulate the short term aging. Then we will come to the testing. So in order to simulate short term aging, there are two protocols: thin film oven testing and rolling thin film oven testing. Have you done this test? You might not perform this test. This is a simple oven. There is a horizontal plate. You can see here, and then we have some small plates. In this plate we will put around 30 grams of binder, and then we will put in this larger plate, and this plate will rotate with a speed of 5 to 6 rpm. At the same time we will expose a high temperature to it. That temperature will be around 165 degrees Celsius temperature, and we will keep this binder for 5 hours, and that is going to simulate our short term aging. Now in this test you see we require 5 hours of time, and nowadays nobody has time. So in order to reduce the time, there is a modified test version of this thin film oven test, that is called as rolling thin film oven test. Now in this rolling thin film oven test, you have a vertical cage in which you will put your samples. Now we'll put our samples in some glass jars, and this glass jars will keep here, and we will blow air at 163 degrees Celsius for 85 minutes inside this oven. During this process, this cage will rotate at the speed of 33 rpm, and because of this rotation, the binder will rotate around the tube. If you rotate this whole tube, the binder is going to rotate inside this tube, and that will create a very thin film of binder on the surface of these jars, and that is why the name came as rolling thin film oven test. And because the surface area is more, so that is why we are going to achieve aging at the shorter time period. So that is why the test takes only 85 minutes of time in order to complete. This is the real pictures of rolling thin oven test. You can see here the vertical cage, and these are the glass bottles in which we will put our samples. Then the next aging scenario is the long-term aging. Now long-term aging, that means aging after your service life of the pavement, maybe after 10 or 15 years of time. Now in order to simulate this 10 years of service life of the binder, we use a pressure aging vessel. Now pressure aging vessel is something kind of your pressure cooker. We will have some plates, and we will put your binders in your plates, and then we will put them inside a pressure cage. We will maintain a temperature of around 90 to 100 degrees Celsius, and then we will apply a pressure of 2070 kPa, and we will keep this for 20 hours of time. This gives a simulation when binder gets aged after 10 or 15 years. So till now what we have seen that binder will undergo different temperatures. Those temperatures are 0, 25, 60, 135, and we have seen the binder will undergo 3 different aging label, which are 0, which are short term, which are long term. Now let's come to testing and try to correlate with these conditions how our tests are being designed. So whenever we have minimum temperature, your binder will behave like an elastic solid. Elastic solid means a material which follow which law? Hooke's law. If you come to the average temperature, the binder will behave like a viscoelastic solid. Now I will not ask what viscoelastic solid is. If you further increase, the binder will become viscous liquid, and if you further increase, it will become a liquid. So the first test what we do to characterize the binder at ambient temperature, that means at viscoelastic domain, that is the penetration test. Very basic test. Today you might have performed the test. Very basic. We will put binder in some container, and then we will take a needle. We will apply a 100-gram load for a 5 seconds of time at 25 degrees Celsius temperature. This is what penetration is. So you try to connect whatever this test is trying to do. It is trying to measure the viscosity of this material at 25 degrees Celsius in some other terms. However, the repeatability of this test is very poor. Whenever you may have performed, you may have realized that the results will not be consistent. The next test is at higher temperature, and that is to ensure the safety, because in the field we are going to heat our binder, and we need to restrict that the binder should not be heated more than this temperature. And in order to find out this temperature, we do this flash or fire point test. I think you must have been performed this test. Then this ductility test. Now I have kept this ductility test on the unaged sample only, but however this 2013 version of IS 73 has kept this test after short term aging. Okay, so just take care of this. So in ductility, we will put our binder in some standard briquette, and then we will try to stress them with some standard rate. Now what property this signifies? Ductility, but in practical, what ductility means for a civil engineer? It signifies the coatability of aggregate. That means how much this binder is going to coat your aggregate. This coatability is being taken care by this ductility. Then we have a test called absolute viscosity. Absolute viscosity we normally perform using Canon Manning viscometer. Have you performed this? Okay, so this kind of tubes are there. So this is actually the Canon Manning tube, in which we will put the binder and we will keep it at desired temperature, which is 60 degrees Celsius, and then we will apply some standard pressure, that is a 35 mm of Hg, and because of the pressure the binder will flow, and we will record how much time it is taking to cross this mark to this mark and this mark to this mark. The average of these two multiplied by the constant of this tube will give you absolute viscosity for your binder at 60 degrees Celsius. Now this is very important for viscosity grading, because what numbers you get, Vg10, Vg20 or Vg30, that is because of this test. Then one more test we do for viscosity, that is a kinetic viscosity, and that we actually do at 135 degrees Celsius, and that is to signify the mixing and compaction. Now for that we use normally a Canon Feskin tube. So here we will load our binder in this bulb, and then we will allow it to cross through these lines, and we will note time when the binder crosses these lines. Again, that time multiplied by this tube's constant will give you kinematic viscosity of the material. Now, but how this absolute viscosity and kinematic viscosity are different is why we are measuring these two viscosity. We can measure the absolute viscosity at 135 degrees Celsius also. So what is the reason to characterize a kinematic viscosity? So first differentiation what you people need to make, that in absolute viscosity we have applied an external vacuum in order to make the binder flow. But in this case we are not going to apply any vacuum or any external force in order to make our binder flow. The flow is occurring because of gravity, and this is the actual case which happens when you will mix your binder with your aggregate. So that is why the kinematic viscosity is the real measurement how your binder will behave when you will mix it with the aggregate. Then the next type of testing on the neat binder what we do is the softening point test, or ring or ball properly known as. So here we take samples on two rings, then we will keep them at a 5 degrees Celsius, then we will start testing, and at the same time we'll put these balls of around 3.5 grams and whenever these balls touches the bottom of this frame, that temperature we take as a softening point. So this softening point is actually an indirect measurement of some viscosity. A viscosity means a particular viscosity when a binder attains. That temperature we want to signify. So it's the reverse of penetration. In penetration, we measure viscosity at 25, but here we want to measure a viscosity, a particular viscosity attained at what temperature. Based on these tests, the IS 73 code is being formulated. You can see the 4 different codes: VG10, VG20, 30, 40. All the properties what we have discussed: the penetration, absolute viscosity, kinetic viscosity, flash point, solubility test in trichloroethylene, that means how much purity it is, then the softening point, and then you can see here the test on the rolling thin film oven that I told you, the short term aging. So these 2 tests you have to do on the short term age samples, not on the neat samples. So those are the viscosity ratio and the ductility. Now we have done this grading very good. We have VG10, 20, 30, 40 binders. But whether these gradings are fair enough to separate out the different types of binder, to understand, let's see this graph. Now we are grading our binder based on the viscosity at 60 degrees Celsius. So here if you can see, all these lines have the same viscosity at 60 degrees Celsius. However, their penetration values are different, their performance at cold temperature is different, and their performance at high temperature is different. So should I grade all these binder as a same VG gauge binder, or I should come up with a different grading criteria? So this is the biggest question what our pavement material peoples are dealing with, that how to modify this grading system in order to account these problems. So there are some advantages. We are doing some fundamental testing. We do testing at maximum service temperature. We include high and average service temperature, but there are some disadvantages: harder to run, more expensive equipment, doesn't specify long-term aging, doesn't consider low temperature cracking. Now the main problem what we are doing, that fundamentally where we are wrong. So whatever the test we are doing, we want to signify, we want to check the properties at 60 degrees Celsius. But this is not the case. Let's suppose you want to design a pavement at Indore. So you want to check at Indore's temperature a particular performance is meeting or not. But you are checking it in another way. You are checking whether at 60 degrees Celsius what performance is being delivered. So this is the fundamental problem. Instead of, we need to check a particular performance met at what temperature. So to address this thing, US came with a very high monetary scheme called SuperPave, and they gives a SuperPave specific. Sir, interrupt कीजिएगा जब time हो जाएगा. So US came with a very huge funding, a project called SuperPave. SuperPave means super performing pavement. Now in SuperPave there are more realistic testing which is being included, and we try to signify the performance of the binder based on their service temperature rather than the performance at 60 degrees Celsius or at any other temperatures. So this program actually came around 1992 in US, and today in India we are trying to adopt the partial form of that thing in India in our code, and that partial thing we are going to discuss here. We will not discuss the SuperPave grading system. So that partial thing, what we are trying to adopt is, we want to simulate the condition at supply, that means at zero aging, during production, that means at short term aging, and after long term aging, and we also want to check the performance at rutting and cracking. So in order to check that, first let's see the set of tests and let's see how they will be connected. So the first test is the high temperature testing, that is around 135 degrees Celsius or maybe 160 degrees Celsius. That means you at your mixing and compaction temperature. And now this test is being done by a rotational viscometer. I will not go into the rotational viscometer scheme what it is, but it is have some kind of a spindle. You will have fluid filled in a container, and this spindle is going to rotate inside the fluid. Your motor will try to rotate it with a constant speed of 20 rpm or whatever is desired. The amount of energy required to rotate this motor will signify your viscosity. If higher amount of energy required, that means the viscosity is higher, and if lesser energy is required, that means a lesser energy, lesser viscosity. Then the next biggest improvement which is being brought in the form of dynamic shear rheometer. Now what we have discussed that in service temperature, our binder behaves like a viscoelastic material. Now viscoelastic material is a material which has both the properties partially. They can behave as a viscous material also, as an elastic material also. So in order to characterize that viscoelastic nature, this DSR testing is introduced. Now in this testing there are two plates, if you can see, and we will put our binder inside this plate and we will try to load a oscillation loading on this sample. That oscillation loading means will go this type. Clear picture will be there in the next scenario. So this is the equipment picture. काम नहीं कर रहा है. So here you can see two plates. So we'll put our binder here in between these two plates. This is the kind of sample of the binder required, and then we will try to load the binder. The loading will be this plate will move from A to B, B to A, and then A to C, and then C to A. That means half rotation this side, then again a half rotation this side. So this will generate a shear on the binder, a half shear, then again a half shear. So if we discuss about the elastic material, you know Hooke's law, stress strain curve is straight line. That means if you put some load, at the same proportion you are going to see the strain immediately. And if we discuss about some viscous material, if you put stress, the strain will be developed after 90 degrees of lag or 90 degrees of phase angle. And our viscoelastic liquid or viscoelastic material will be in between of these two. So if you load your binder with some stress, the strain will develop, but after some time, and that time lag is known as phase angle, delta, and the ratio of whatever the maximum or minimum stress upon the maximum and minimum strain is called as complex modulus. This is similar to your elastic modulus or Young's modulus, whatever you have seen. So here this complex modulus we signify as a complex number. Now in this complex number we have two components. As I told you that viscoelastic material will show a viscous and elastic behavior. So we will try to separate out this viscous and elastic behavior separately. So there will be a viscous modulus and there will be a storage or elastic modulus, and this delta is your phase angle what you have calculated, and modulus of these two will be your complex modulus. Now this complex modulus is very important parameter which will signify all the properties. Now once you have estimated your complex modulus and phase angle, you can calculate a rutting parameter as specified by FHWA, which is your complex modulus divided by sine delta or sine phase angle. Now what it signifies, if you see your G star is higher, that means your material is more stiffer. More stiffer, that means it will undergo less rutting or less deformation. And if your delta is low, that means your material is more elastic. So what you want? You want better stiffness and more elasticity, isn't it? From a binder, you want whatever the deformation is there, that should recover quickly, isn't it? So we want more elasticity property and high stiffness at the same time. Similarly, we have the next parameter, which is G star sine delta, which we known as a fatigue parameter. Now again here G star is higher, this one delta is higher. So lower value of G star sine delta means the lower potential of fatigue. So in DSR testing on unaged sample, your G star sine delta value must be exceed 1 kPa for unaged sample. Then the next test what we will perform is the separation test. Now separation test, because we are adding something into the binder, so that admixture or that mixture what you have added, that should be uniformly distributed inside the binder. But what happens, because of the gravity, if there is not good mixing of admixture with the binder, there is not good cross linking, then in that case your additive will try to deposit at the downside because of the gravity, try to settle down. And in order to make good binder, we don't want this settlement of additive. In order to characterize that, there is an stability test. In the stability test, we will put our binder inside these types of aluminum tube, and then we will keep for 24 hours at elevated temperature, and after that 24 hours at freezing temperature. And then we will cut the bottom part and the top part, and we will check the properties of top and bottom. The properties of top and bottom should not differ too much. The next test on neat binder, what we will do for polymer modified binder or any modified binder, is the elastic recovery, similar to your ductility test. Here we will take, but this briquette is different actually. So we will take our binder in this briquette and we will stress them to 15 centimeters of distance, and after that we will cut the binder. Now if there is elastic property, it will try to regain its shape. We will try to check out how percentage shape is regained by this binder, and that will be known as the elastic recovery. The next test at 0 degrees Celsius, this is the only test. Now we have more sophisticated tests to characterize at 0 degrees Celsius, but we are not going to discuss that. This frost breaking point is a test which you can do to characterize binder at low temperature. So there is a small film. In the film you will coat your binder, and then you will decrease the temperature. Temperature may be 0 or minus, and after every 2 or 3 degrees Celsius decrease, you will try to press this so that this sheet becomes bent. Now whenever binder attain a certain brittleness, due to this bending the binder will crack. The point binder cracks, that points will be taken as the frost breaking point. Then on short term age, what short term aging is we have already discussed. So on short term age, what test we will do, that will be G star by sine delta, and on short term sample the value of G star sine delta should exceed 2.2 kPa. all whatever the test we have done, that test isn't characterized the viscoelastic nature correctly till this point. In order to avoid all those things, a new test is being introduced now, that is known as MSCR, or multiple stress creep recovery test. This is similar to your triaxial test. So here we will try to load the binder for 1 second, and then we will give a 9 second of resting time. Again we will load, give 9 second of resting time, this 10 cycle, and then we will increase the load to 3.2, and again we will repeat a 10 cycle. Now if it is a elastic material, how the graph should be? If I have loaded, immediately the curve will come down here only. So whatever the stress curve is, similar will be the strain curve. But this is not a elastic material. So whenever you have applied load, the strain will develop with time. And when you have removed the load, the strain will recover partially, but not fully, because this is not an elastic material. So again, if you do, so at each last of each cycle, there will be some accumulated strain, and that will be keep on adding as you increase the number of cycles. Based on this, you can define certain term. So whatever the recovered, that you can call as a recovered strain, and whatever is not recovered, you can call as unrecovered strain. Based on this, we can define a index called JNR, which is a function of unrecovered strain upon the applied stress, and the difference between whatever the two loading we have applied, because here you can calculate 2 JNR when you have applied 0.5 kPa of load, and JNR when you have applied 3.2 kPa of load. So the difference of these two is called JNR difference. Then on long-term age sample. So on long-term age sample, we will do a testing for G star sin delta, and for G star sin delta PAV binder, the value should be must be less than 6000 kPa. Based on all these tests, this is the specification table of polymer modified binder. So based on Indian standard, we have currently 5 polymer modified binders, which are PMB 6010, PMB 7010, PMB 7610, PMB 8210, PMB 7622. Now what it is? It is PMB 6010 means this is the binder you can use where the maximum temperature is less than 64 and minimum temperature is higher than -10. Okay, like your PMB 8210, that means the maximum temperature should less than 82, and this is the pavement temperature I am talking about, not the air temperature, and your temperature should be higher than -10, and you need to satisfy all these properties which we have discussed in previous slides. Now how to determine the pavement temperature, because you cannot directly measure the pavement temperature. So for that, a empirical equation is given or suggested by the IS code. Now that empirical equation is based on the air temperature and latitude of the region. So if you have the air temperature of the region and latitude of that region, you can estimate the temperature at 20 mm depth of the pavement. That will be input of your grading. So based on all this information, we have these grades of binder which you have already seen, the 5 different grades. Now the question is, we have signifies the temperature, but is signifying temperature is enough to cater the need of traffic, to cater the need of load or loading on the road? No. Even if temperature is low but your load is very high, then pavement demands a higher grade of binder. So in order to do that, there is a concept of grade bumping. Now what grade bumping is, let's suppose I have a region where I have temperature in the range of 64 and -10, but I have a very heavy or heavy condition of traffic. So instead of whether my temperature is 64 minus 10, but instead of selecting this grade of binder, because my traffic is heavy, so I will just go one grade up. This is called grade bumping. If traffic is very high, I will again increase one grade up. So even if temperature scenario are lower but traffic is high, then the grade bumpings need to be exercised. Similarly, we have natural rubber modified binders gradation. I will not go into it. They are similar. Now we have only two types of natural rubber modified binders, that are CRMB 70 and CRMB 40. But all those testings are not defined here for the CRMB binder because of the grain size of the crumb rubber modified binders are higher or bigger as compared to the polymer modified binder. So normally when we do a DSR testing, so the air gap between two plates is 1 mm or 2 mm maximum, but the grain size sometimes bigger, higher than 1 mm. So the testing is a kind of doubtful in the case of CRMB binder. So again, people are working to modify this grade, and there is a group of people along with the Central Road Research Institute and IIT Delhi. They are currently pursuing a project in order to make a full-fledged super pave grading system, including both CRMB and polymer modified binder. And I am also a part of that. Some testing I will also perform. Okay, so that is from my side. Hope it might given you something what you don't know. Okay, thank you.
Thank you, sir. It was a wonderful and thoughtful session. Now, I would like to invite Professor Vijay Baradia, sir, for presenting the memento to Dr. Priyan Singh, sir. I would also like to invite Ms. Pallavi Gupta, ma'am, for presenting the memento to Pritesh Mahajan, sir. Now, I would like to invite Mr. Divakar Singh, sir, for the vote of thanks.
Thank you, Manya. Good evening, everyone. As we come to the conclusion of the in-flight food skill development training program, I would like to take a moment to express my heartfelt gratitude on behalf of Civil IPSA family and IGS IPSA IES student chapter. Firstly, I want to extend our sincere thanks to our esteemed speaker, Dr. Priyan Singh sir, Assistant Professor, Civil Engineering Department, IIT Indore, for sharing their valuable expertise and knowledge with us today. Your insights on highway material testing have truly enriched our understanding and speakers our curiosity. Dr. Kunal Gupta sir for his session on geotechnical applications. I would also like to thank the organizing team whose hard work and dedication made this workshop possible. Pritesh Mahajan sir and team from Index Laboratory went above and beyond to ensure that everything ran smoothly from planning to execution. A special thank you to our sponsor Indian Geotechnical Society, New Delhi and Indore chapter for their gorgeous support. Your contribution have made a significant difference in the success of this event. Lastly, I want to acknowledge all participants for your engagement and enthusiasm. Your question and discussion have created a vibrant atmosphere that has made this skill development training program all the more enjoyable. As we leave today, let's take the knowledge we have gained and apply it in our respective fields. I look forward to seeing the impact of what we have learned here. I would like to sincere thanks to our President Architecture Ajal Chaudhary sir and impress my principal Dr. Archana Kirti Chaudhary ma'am and HOD Dr. Amit Sharma sir for providing us the necessary facilities for organizing this skill development training program. At last, I would like to thanks to all directly and indirectly involved in organizing this skill development training program. Thank you once again.